Hello everyone, my name is Maya Janson, and today I'm going to be talking about Giardia duodenalis. So for the habitat of Giardia duodenalis, it is found worldwide in areas of poor sanitation and areas with unsafe water. And it's often found in South America, South as well as Southeast Asia, and Sub-Saharan Africa. And to the right of this, I have the map of prevalence worldwide, specifically in non-human mammalian hosts. I included this map because this parasite often undergoes zoonotic transmission, and the prevalence of both non-human mammals and humans is very similar worldwide. For the taxonomy of the parasite, its domain is Eukaryota, the kingdom is Protista, the phylum is Metamonada. The class is Trepomonidae. The order is Diplomonadida. The family is Hexamydidae. The genus is Giardia, and the species is duodenalis. I also included Lamblia and intestinalis for the species because all three are the exact same. They just sometimes go by different species names. The Giardia life cycle is interesting. It's split into two different sections. So you will start by ingesting the dormant cyst, and once that cyst moves down through your stomach into your small intestine, it will undergo excistation and remove its outer shell of the cyst and become into its trophozoite form. In this form, it will undergo replication and cause illness in the small intestine. Once the parasite moves down into the colon, they will turn into their cyst form again, gaining that new outer shell, and be able to survive outside the body for months at a time, ready to be ingested in the future again. Here are the micrographs of Giardia duodenalis. On the left, I wanted to show both life stages of the parasite. On the very left, we have the trophozoa, and then we have the cyst on the right. And you can see that cyst has that very hard outer shell that will allow it to survive outside the body in those harsh climates. On the very right, I have the Giardia duodenalis under a microscopic lens, and it's specifically shown floating on a human intestine. And this is where it will eventually attach to the intestine and gain its nutrients. So for pathogenesis, the parasite will attach onto that intestine line, like I just said, and disrupt the microvilli. This microvilli is what allows our body to absorb the nutrients, and so that disruption is very critical. That disruption will lead to less absorption of fats and carbohydrates, diarrhea, bloating, as well as weight loss. Overall, this will cause villus atrophy, brush border enzyme deficiency, which is when the small intestine lacks enzymes like sucrase, isomaltase, and lactase, which are all very crucial for breaking down carbohydrates. And lastly, this will all increase epithelial permeability. So overall, not good for your body. The virulence factor that I will be discussing is variant-specific surface proteins. They are commonly called VSPs. These VSPs are cysteine-rich proteins that are expressed on the surface of the trophozoite. Only one VSP is displayed at a time, and the parasite will switch VSPs in order to avoid detection by host immune responses. So imagine you're playing hide and seek, and you are hiding from the person who's trying to find you, but you keep on switching places. Basically, you're cheating. So these are big, fat cheating parasites, which are controlled by the RNA interference and epigenetic regulation. On the right, I have this image that you can show, or that you can see, that the antigens are switching from the trophozoite, and it is then attaching onto that epithelial layer of the small intestine, where it will replicate and take our nutrients and continue the cycle again. Now, the CSO explanation would be that VSPs cover the entire trophozoite surface, and this VSP will protect the parasite from complement-mediated lysis, which is when the immune system creates holes in the membrane and causes the target cell to burst. So this can't happen because of the VSPs. They're being hidden the parasite is being hidden by these host antibodies. The antigenic variation occurs because the RNA interference will silence all VSP genes except for one, and overall it will avoid antibody recognition and lead to continued chronic infection. If we were to block VSP switching and stop that process, we would force the parasite to express the same antigen, so no more cheating, and this would allow the host antibodies to eliminate the parasite and be way more susceptible to attacks. The image on the right I'm showing is we start with VSP1, so one antigen is expressed, and then it will change the VSP and come out with a new one, which is then ready to colonize the small intestine and continue replication and infection causing. Now, a physician explanation would be that the VSPs are what are keeping you sick. Since we cannot target the parasite due to its changing antigens, the infection will continue to spread and make you sick. If we were to stop the parasite from changing these antigen layers, your immune system would then find it a lot sooner and destroy it, and you wouldn't get so sick. Now, there's many ways to do this. There's many susceptible drugs. Starting off, there's metronidazole, which is once the drug is inside the body, it will go through anaerobic metabolic pathways, which reduce the drug into its reactive nitroradicals, which will then damage DNA, disrupt nucleic acid synthesis, and lead to parasite cell death. The second one is tinidazole, which is chemically very similar to metronidazole, but with a longer half-life, but it kills the exact same as metronidazole would. Then there is nitazoxanide, which interferes with pyruvate ferredoxin oxyreductase, aka PFOR, which is an enzyme-dependent electron transfer reaction that is essentially the parasite's energy metabolism. This disrupts anaerobic ATP production and the parasite's ability to regenerate oxidized ferredoxin. Then there is albendazole, which will bind selectively to the beta tubulin of the parasite, which disrupts microtubule polymerization, cyst and trophozoite structural integrity, glucose uptake of the parasite, as well as cell division. Lastly, there's kinekrin, which through DNA interlation, the drug disrupts transcription and translation, and then it impairs energy production. So it pretty much just damages the metabolic enzymes of the parasite as well. But the most common treatments are the metronidazole, tinidazole, and nitazoxanide. However, there's a few different ways that the parasite will become resistant to those drugs. Number one is that it will reduce the activation of metronidazole. So as we just learned, the metronidazole needs to be activated by the pyruvate of the parasite, but the parasite can reduce pyruvate activity and overall decrease drug effectiveness. Second, there's the upregulation of antioxidant defenses. This will increase the detoxification of the reactivity of the intermediates of the parasite, and that also decreases the oxidative stress which is caused by the drug, pretty much just making it useless in the end. The third way that the parasite will resist to these drugs is by the efflux pumps, which these pumps that are inside of the parasite, once the drugs come into it, will pump that drug out of it and make it so that it was never drugged in the first place and makes it ineffective as well. Overall, all of this will continue the chronic infection, which is not good. And that is my presentation. Thank you very much.